Everyone, Mr. Smith here, shooting my 5th video of today in the last 4 hours. So I'm still feeling pretty strong. Haven't screwed up too many things. So yeah, let's see if we can keep doing well. Excited to give this lesson. It's really look at some cool applications of centripetal acceleration. And here we're looking at centripetal forces. So let's get started. So a consequence of Newton's second law is that since the centripetal acceleration is towards the center of the circle, then the net force must also always be directed towards the center of the circle. And so if we start from Newton's second law, we kind of get, it's not a different Newton's second law. It is just a Newton's second law where instead of sum of force is mass times acceleration, we throw in what the definition of that acceleration is. So instead of acceleration, we have v squared over r, giving sum of forces. And sometimes we'll use FC for centripetal force. And that can be a combination of forces providing a centripetal force equals mv squared over r. And depending on the situation, whether you have v or the period t or the frequency f, there's 3 different variations of that. Centripetal force equals mv squared over r, or 4 pi squared mr over t squared, or 4 pi squared mr f squared. And these are basically the formulas for centripetal acceleration with an m for mass and acceleration. So we're going to look at, I think, 4 examples and of kind of 4 different examples of uniform circular motion. And in each example, we're kind of want to not only just kind of solve the problem, but think about in each of these, what is actually providing the centripetal force? Or are there multiple things contributing to the centripetal force? So yeah, let's get started. In this example, so we have a car entering a level curve. So just imagine maybe a car in a roundabout or a big open parking lot, just traveling in a circle, okay? So a car driving in a circle. And the way we've drawn the picture here is the car is driving out of our page, looking at, or at least out of our screen if you're watching a video. And the circular motion is coming out of our screen and then back into our screen and out of our screen. And in this case, the direction of the centripetal acceleration, and hence the centripetal force, is going to be to the left on our page. So the car is traveling in a circle. The centripetal acceleration is here. So for these kind of problems, I like to actually just say, okay, AC going that way, and imply that I'm going to choose my positive direction to be that way. So positive, positive. All right. So what forces are acting on this car? Well, gravity, obviously, mg. This car is in contact with the road. So we do have normal force acting up. But this car is traveling in a circle. There is some acceleration. So there is some net force towards the center of that motion, i.e. towards to the left on our page there. So what is providing the centripetal force in this case? If you want to pause the video and think about that, you can just unpause when you're ready. If you said static friction, then you were right. I'm just going to call that FF. But in this case, it is static friction, which is really cool. It is actually possible for static friction to be the sole force contributing to centripetal acceleration. So that's pretty neat. And in this case, we're looking for what coefficient of friction, and we understand here that we're trying to keep the car from moving left or right. That is the coefficient of static friction. Must exist to keep the car from skidding. Because if it's skidding, well, then we've overcome that static friction force and now it's moving. So we're trying to find what coefficient do we have to have so that that car won't skid left or right out of that banked curve. Not a banked curve, just a level road, I mean. So yeah, let's get started here. So we've set the problem up, free body diagram. So let's look at Newton's second law. So the sum of forces equals mass times the centripetal acceleration. And what we have is the only force providing the centripetal force is that static friction equals MAC. Now, I think I didn't take my own advice. And usually we analyze things in the y direction. Why do we do that? Because for problems involving friction, that involves a normal force. So we'd often like an expression for the normal force. So very quickly doing that, the sum of forces in the y direction equals mass times acceleration in the y direction, which is of course 0. And we chose up to be positive. So Fn minus Fg equals 0, or mg. So Fn equals mg. Fg and mg being equivalent. So yeah, should we usually do the y direction first if you're doing a friction problem. Let's actually, for this one, plug in what that definition of force of friction is. So it's mu s times Fn equals MAC. And let's plug in a few more things we know. So Fn is equal to mg. And we don't know the centripetal acceleration of the car, but we're given information about its speed. So we're going to use this version, mv squared over r. So a reason why I didn't actually calculate the normal force is because we didn't actually need it. The mass of the car is actually irrelevant because you have a mass on both sides here, it divides out. And the coefficient of friction required to keep it from skidding is v squared over g times r. And we can just calculate that. So that means that the coefficient of friction necessary to keep a transport truck from skidding is the same to keep a little compact car from skidding. And so we get 20 squared divided by 9.8, and the radius of the curve we said was 80 meters. Uh, 400 divided by 9.8 divided by 80, so about 0.51. All right, so the big idea in that question, so our first example with looking at centripetal forces, is that static friction could provide the centripetal force in the case of a car traveling on a flat road. Let's look at another example. Here we have a car on a banked curve. And so in this case, we have the same car, but we have a frictionless banked curve. So to keep things simple, we're removing friction from the problem here. And I'm not sure, maybe you've watched NASCAR, or maybe you've experienced this driving on the highway. But sometimes when you're doing a curve and you might be traveling at a fast speed, the curve is banked a little bit. And there's a reason for that. And the reason is because it can help you traverse the curve safely. By banking the curve, you don't have to rely on friction to provide a centripetal force and allow you to keep turning. So we're going to investigate that right now. So we're going to ask, given the dimension of this curve, so it's a 20-degree banked curve, and we have a 1,000-kilogram car, we have the same radius of motion, 80 meters. How fast can we go into this curve safely? So if we were like a civil engineer and we had to, get the signs printed up, danger, don't travel above this speed, we can do that. So let's check this out. So the centripetal acceleration is towards the center of our motion. And again, we are imagining the car coming out of our screen, traveling around the bank and then back into our screen. So the acceleration, as far as the diagram is set up here, is to the left. is that centripetal acceleration. What that means is we're going to have to go against the grain a little bit. We just finished up our unit where we looked at inclined planes, and often the motion on an inclined plane was up or down the plane. We chose our directions to be parallel or perpendicular to the plane. But in this case, the acceleration is actually not parallel with the plane. It's just to the left. So for our sign convention, I will use up and left. And that means I will not be resolving gravity in the components up or down the ramp, because it's vertical, and I want my components to be left and right because the acceleration is horizontal here. So we have gravity. We don't have any friction. So if you haven't thought about it yet, what's the last force we haven't added to our diagram, and what force is actually contributing to the centripetal force? What force is the centripetal force in this case? If you said the normal force, you'd be right. It's actually the normal force, or a component of the normal force here, that is contributing to the centripetal force. The normal force here, because the curve is banked, is actually up and on our page to the left a little bit. And there is a component of that to the left, and that's providing the centripetal force in the absence of friction. So that's pretty cool. I think maybe on here I can squeeze this in. So if the angle here is 20 degrees, so we want to actually reason out what's the angle between the normal force and the vertical here, so we can actually get an expression for the normal force. So I hope you would agree, if that angle is 20, this angle tucked in here would be 70. And the ramp and the normal force are always perpendicular, right? And that's 90. Well, 70, 90, what's left is that this angle tucked in here is 20 degrees, making the kind of horizontal component, I'll call it Fnx, is equal to Fn, and it's the opposite, is across from 20, so it's sine 20, and Fny, this vertical component of the normal force, is Fn times the cosine of 20. And we're now ready to solve this problem. In this case, with no friction, we don't really need to, we're not asked to calculate the normal force. Actually, I think we will need to calculate the normal force, because we want to find the speed necessary. So we do need the normal force. Yes, we do. So let's look at the y direction. So the car is not flying up in the air or going down into the ground. So the sum of forces in the y direction is 0. And in the y direction, we have two things going on. We have Fn cos 20 and gravity acting down in the negative y direction. And if we solve this equation for Fn, moving mg over and dividing by cos theta, we get an expression for the normal force. So if you recall, maybe when we were doing some review lessons or doing some problems involving the normal force, I took some time to say, hey, the normal force doesn't always act up, and it's not always equal to the weight, mg. Sometimes it's different. Here, it is one of those cases where the normal force is acting up and left while gravity is straight down, and the size of the normal force isn't mg. It's mg divided by cosine 20. So we could calculate that, but I think, you know what, guys? I think I'm going to leave it as in a general sense right now, and you'll see why in a second. So we definitely could calculate the normal force, but often, sometimes just getting an expression for it is enough. You'll see why in a second. So in the x direction here, we have the sum of forces. We do have some acceleration, the centripetal acceleration, and we want to find a maximum speed. So the sum of forces, there's only one. It's Fn times sine 20. And let's use v squared over r. So mv squared over r, v squared over r for AC, because we're trying to find that v. I'm just going to do my work up here. We have an expression for Fn. Fn is equal to mg divided by cos 20. So we're left with mg. We still have the sine 20 there, divided by cos 20 equals mv squared over r. And the reason why I didn't calculate the normal force was because when you write it in, when you sub it into this equation here, the mass actually divides out again. And this is another question where the mass of the car was actually irrelevant. And we can solve this for v. So to get v squared by itself, you would multiply up the r. So you get g times r times sine 20 over cosine 20. And then that's v squared, right? So to get v, we would square root it. So I actually just showed it an extra step there. So it'd be the root of g times r. And because most of you guys have done the grade 11 math course, I think it's reasonable for us to make this even simpler. The sine of 20 degrees divided by the cosine of 20 degrees is actually the tan of 20 degrees. And I might just add, in general, it would be the root of gr tan theta, whatever the angle of the incline is. So yeah, let's find out, guys. What is the safe speed for this ramp? It depends on gravity. Depends on the radius of the curve, which is 80. And it depends on the tangent of the angle of inclination, which for ours is 20. So we get, and keep in mind, this is going to be meters per second. So 9.8 times 80 times tan 20. And root it. So pretty much 17 meters per second. If you multiply that by 3.6, maybe it's about 61 kilometers per hour. So about 60 kilometers per hour is kind of like maybe the top speed you go around in. If I were a civil engineer, I'd probably take a good percentage of that off and recommend that people go around this curve maybe at something even less, 50 meters per second. So we got that speed required. And I'd like you guys to think about, if we decreased our speed, what would happen? Would we go down the ramp, or would we go kind of go down the incline or up the incline? So if you look at our equation here, think about how v and r are interchanged with each other. If I was to increase r, just by the nature of the equation, right? If r is bigger, then v gets bigger too. And if r gets smaller, v gets smaller. So if we're looking at what happens if we decrease our speed, if you have a smaller v, you get a smaller r. So if you decrease speed, decrease radius. So what would happen would be you'd start to move down the ramp a little bit. And if you sped up, if you increased your speed, you increase the radius, and what would happen is you kind of go up the ramp. And if you've kind of watched NASCAR or had this experience, if you come into a curve like too fast, you do kind of go up the ramp and are in danger of like going over the guardrail. All right, and finally, if we increase the bank angle, what happens to the maximum speed? So you could try this on your own. So here was 20 degrees. If you were to do this calculation for, say, 30 degrees or 40 degrees, what you would find is that as you increase theta, so as you increase theta, the tan of theta goes up too, and you increase the speed, which means as you get a steeper and steeper curve, you can actually travel faster and faster. So that's why at NASCAR, their banks on curves are you can't see my hand, they're very steep to allow the cars to go around maintain a very fast speed. Maybe even seen those people in motorcycles in those big circular cages, maybe at a circus, and almost they can ride their motorcycles horizontally around a wall. That's because they're so banked that they can travel at a very high speed. So it's very interesting. I say here too, what speed would be required if the frictionless bank were at 90 degrees? If you try to do tan of 90 degrees, just try it on your own. tan at 90 degrees is undefined because tan just keeps going and going higher and higher until you get to 90. So the tan of like 89.9 is like some very, very big number, which means to travel in uniform circular motion along basically a vertical wall, you would need to be needing to traveling at an infinite speed. So for a very, 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 very steep curve or basically a wall, you need to be traveling at a very high speed. So those were just all kind of interesting discussion questions. But the big idea for this question is it is possible for the normal force to provide centripetal force in the case of a banked curve. Now, in reality, both friction and having a banked curve can help provide centripetal force. So in reality, it's a combination of both of those things that can keep a car safely traveling in a circle. All right. Let's look at a third example. So most of you guys have probably seen a loop-to-loop, maybe on a roller coaster. I've got a little QR code there. If you snap that, you should be able to check out the link there. So at the time, this was the largest loop-the-loop done in a car. So I won't play the video here. You can go check that out. It's like 3 minutes. It's from the Guinness World Records TV show. So it's kind of entertaining. But yeah, you should definitely watch that. And a really interesting question is, how fast does a car have to travel in order to safely make it around a loop-the-loop? So here we have a loop-the-loop. And the step of the question says that the diameter is 12.87 meters, which would mean the radius would be half of that. So let's just get this set up, 5 by 2, so 6.435. And we're asking ourselves, how fast do we have to go around this? Now, what you have to keep in mind is that the car going into this loop-to-loop is not going to maintain the same speed all the way around. In reality, the car gets up to an incredibly high speed, and as it goes around the loop and starts to go up, it actually does slow down. So what we are going to be assuming, and I mentioned this earlier, we're going to be just basically analyzing just the top part of this motion and assuming that it's uniform circular motion. So we know the motion's in a circle, but we're going to assume that the speed is constant, and we're going to analyze it right at the top. So this one doesn't take a lot of work at all. I'll ask you guys, let's make a free body diagram. I'm going to make it right on my image here. What are the forces acting on the car, or what are the forces providing the centripetal force? And you can ignore friction for this case. We'll just pretend it's frictionless. But even if there was friction, wouldn't really matter. Well, we obviously have gravity going down, and we have something on a surface here. Which direction would the normal force be? This is a situation where the normal force would be down as well, in the same direction as gravity. Remember, the normal force is always perpendicular to the surface, and the surface here is this vertical part of the loop. And the centripetal acceleration is, I don't want to squeeze this in there, but at that point, it's also towards the center. So we have two things contributing to the centripetal acceleration. Let's have a look at this. So sum of forces equals mass times and centripetal acceleration. And here we have two things contributing to that, mg plus Fn. And we're looking for a speed here. So m, we'll use v squared over r for AC. Now, here's the thing with this question, with the vertical loop-to-loop. We're finding the minimum speed. So at the top of the loop, that minimum speed, the slowest that car could be going, if you imagine what happens if the car is not going fast enough, it falls off the track, right? And if it falls off the track, what do you have for a normal force? It's 0. If the car loses track contact with the surface, the normal force becomes 0. So we're finding the V that makes Fn equal to 0. So find the V so that right at the top of the loop, that normal force is 0 just for a moment, and the car kind of loses contact, but then as it goes back down the loop, it picks back the track up again and doesn't fall off. So in this kind of problem, we actually set the normal force to be 0. And we can see that we don't even need the mass of the car. And the minimum speed required, you multiply the r up, so you have g times r, and you square root. So pretty cool. So it's actually a pretty, for a kind of a complicated question, math-wise, it's a pretty easy setup. What speed does he have to be going? We'll do the root of 9.8 times 6.435, and we'll convert that to kilometers per hour. Don't forget to square root. So I got 7.9 meters per second. If you multiply that by 3.6, it's basically like 29 kilometers per hour. And that's the minimum speed. Then you may be thinking, hey, hold up. If I have a car going into a loop at like 30 kilometers per hour, there's no way that it's going to make it around the loop. And that's not what we're saying. We're saying the car has to enter the loop, and then as it slows down around the loop, at the very top, the slowest it can slow down to is about 29 kilometers per hour in order for it to continue along the loop and not just fall off the top. So that's what that's saying here. So yeah, pretty interesting problem. So in this case, there were two forces at the top contributing to the centripetal force. It was gravity and the normal force. And in the case where they're at that minimum speed, that normal force was equal to 0. But a big idea is that more than one thing can contribute to centripetal force. Let's take out one more example like that. So here we have a steel ball. It's connected to a rod, and it's being swung in a vertical circle. As we swing that ball, top and bottom, I want you guys to think about where the tension in the rod, and you can imagine, you could do the same problem assuming it was a string, like a yo-yo or something. Where is the tension greatest? Point A or point B? Or is the tensions the same? So we're going to analyze this and calculate the tensions and see which is true. So let's do the top first. Let's do point A. So I'm just going to draw, here's my ball. When the ball's at point A, what forces are acting on the ball? Well, we've got gravity going down, so mg. And the tension in the rod will also be going down, and I'll just call that Ft. And I'm going to call it FTA because right now we're making the assumption that FTA and FTB, the tensions at the top and bottom, might be different. So they might be the same. It might work out that way, but I'm going to label it as FTA for now. And that's it. And at the top of the loop, what's the direction of the centripetal acceleration? Downwards towards the center of the circle. So let's analyze this. So sum of forces equals mass times centripetal acceleration. We have mg and FTA acting in the same direction. And we're going to use the version with frequency since that's what we were given. 4 pi squared mr f squared. And if we rearrange this for the tension, we get 4 pi squared mr f squared minus mg. And we actually have all those things, so we can calculate it. So 4 pi squared, 3.5, radius is 1.5. Squeeze this in here, 1 squared, and then minus 3.5 times 9.8. So hopefully you guys manage your space better than I did there. So 4 times pi squared times 3.5 times 1.5 times 1 minus 3.5 times 9.8. So 173 newtons, roughly, is the tension in the rod at point A. So does that change? at point B. Let's look for point B. I make my free body diagram just below here, just to make sure I have room. So at point B, what's happening? This is at the bottom of the loop. Gravity is always down, right? mg. At the bottom of the loop, the rod is now above the ball, and the tension will be going up. So this is called, we'll call this Ft for point B. And those are the only two things going on. Again, there's no surface here, right? So there's no normal force going on here. And the direction of the acceleration, in this case, would be up towards the center of the circle. Let's set up Newton's second law and see what we get. So sum of forces equals mass times acceleration. Here, we have FTB minus mg. There is a difference between the two. And again, it's 4 pi squared mrf squared. And let's find out FTB. This time, it's 4 pi squared mrf squared plus mg. Four pi squared, 3.5, 1.5, 1 squared plus 3.5 times 9.8. So let's give this a go. 4 times pi squared times 3.5 times 1.5 plus 3.5 times 9.8. So we had a tension of about 242. So if you predicted that the tension would be greatest at the bottom, good for you. You were right. Another way to think about this question is, if you were spinning something around on a string, would be, when is it more likely to break, at the top or the bottom? And the tension would be greatest at the bottom of the loop, and here's why. At the bottom of the loop, you have gravity and the tension acting in opposite directions. So to provide the same constant centripetal acceleration in terms of magnitude, you would need a bigger FTB, because at the top, the gravity force and tension are working together. And so you don't need as much to add to get to that constant acceleration. So yeah, in general, spinning something on a string or a rod, the tension is going to be greatest at the bottom. That's where it's more likely to snap. And we just kind of showed that numerically. And so in this question, guys, it was tension and or gravity contributing together to provide the centripetal force. So those aren't the only 4 examples. In fact, when we talk about satellites and the solar system, etc., it will be gravity providing a centripetal force. But here we've got 4 examples. I think it's a good start, good starting point. So next up, we have a short lesson on frames of reference, revisiting those. And we're going to talk about the difference between centripetal and centrifugal forces. Afterwards, we're going to apply uniform circular motion to things like satellites, planets, binary stars. It'll be a lot of fun. Until then, guys, stay well, have a great day, and we'll see you soon.